All right, good afternoon.
Hey, Mr. Strong.
Hey,
I
how's it
am like
going?
I'm doing like this interview thing with Mrs. Heister. Like she's interviewing all the talent kids. I'm
Okay,
gonna go next real quick. I'll be back in like a couple minutes.
okay, all right.
Okay.
All right, there's Jada. How are you?
I'm good.
Good. All right, well, so anything going on with you guys today? Anybody going, either of you going to the Avengers this weekend?
I am.
Oh, yeah? How about you, Jada?
Yeah, I think I am too.
All right, well, that'll be cool. Um, yeah, I found out that the Roxy here in Holbrook was doing a special showing of the Avengers tomorrow morning at 8 a.m. And so I tried to take my calculus class on a field trip. And would you believe the principal turned me down? I mean, what kind of garbage is that, huh? It's all messed up. All right, so Tobias, are you back or are you? Oh, hey, how are you doing?
How's it going?
Good,
Tell
good. You're
little
coming
video.
to hang with us today? Take notes for Toby?
No, he'll be back in like 2 minutes.
Oh,
I was too big of a distraction, so I had to come in here as a timeout.
yeah, that's all right. That's okay. All right. Well, yeah. So I was really wanting to take. I thought that would be cool to take a calculus class to see Avengers, and we need to get Miss Heister to approve a field trip for us. I think at the end of the year. So anyway, hey, how are you doing?
Good, how are you doing?
Good, good. So I saw you play softball the other day.
Yeah, that was like my worst game ever.
Oh, you didn't play bad. You got somebody out at first.
Did I?
Yeah, yeah,
Oh,
and
I don't remember that.
yeah. So you were anyway. But yeah, it seemed like you guys you were just beating on Joseph City like there was no tomorrow. So,
Yeah, our coach wanted us to make a statement before state.
okay. Well, it didn't have to be against them. Like I know people on
It
the
just
other
happened to
team.
be Joe City.
Yeah.
Huh?
Well, they got. I know it was their baseball team that got messed over in because they were supposed. They were anyway. One of the teams had to forfeit, and so I guess you don't get the same points in the power rankings or whatever.
Oh,
I heard about that. That sounded really bad.
ooh, that stinks.
Yeah. So yeah, they're anyway. The team they were playing didn't even like have the field ready. They didn't have enough players. It was pretty
Wow.
bad. And the players were yelling at the coaches, and anyway, it was just kind of an ugly thing.
Jeez. That stinks.
You don't ever yell at your coaches, do you?
No.
I hear Julie yelling.
Actually,
Really
yesterday I gave my coach some sass. She's like, put your catching gear on. I was like, no. She's like, I was like, oops. I was just kidding though.
Well, don't ever sass your professors in college either.
Okay. I won't.
Well, tell Miss Heister when she's done interviewing you guys that I need to ask her a question really quick before she goes. Okay?
Okay.
All right. See you,
Just
Mr. Brown.
whenever she has time.
Okay. Bye,
So-
Mr. Strong.
All right. Well, good to see you. Good luck at state.
Thank you.
All right. So, Jada, are you on the softball team?
No,
And
I
West Side-
run.
Go ahead.
I did run, but I was supposed to do track, but I didn't do track.
Oh,
I got too
okay.
busy.
And Weston, I know you played baseball last year. Do you play this year?
That was John that played it last year.
Oh, that's right.
Yeah.
That is totally right. Huh. Well, anyway. So do you play?
No, I do track actually, so.
Oh, okay. All right. Well, that's okay. There's nothing wrong with track. So, but anyway, okay. So before we start in on our lesson, let me just show you a couple things here. First of all, remember I told you that I was wanting to link the course improvement survey, that I wanted to be able to give you 5 points extra credit on quizzes for doing that survey. Turns out I can't, because it's not considered an assessment. It's not a graded thing. So I can't make it extra credit. So what I did is right below it. So this is right before the first chapter stuff. So right below course improvement survey, it says extra credit for survey. So what I did is I created this little extra credit quiz so that basically it's one question, true or false. I took the course improvement survey. And so you do true and you get 5 points extra credit. Okay, so once you've completed the survey, you just click on that and then you can get the points. All right? We good with that? Okay. All right, the other thing I did want to show you is I populated the area for the final exam. Now I put the extra credit evaluation stuff that we went over last time. I put that up there. Now you can't see the actual final exam yet. See where it says hidden from students? So you can't see the final yet. So don't even try to hack in there or anything. Okay? But I did put up a practice final just in case that you want to look at some problems or some topics. And then what this is actual, as students have asked me questions, then I work out the problems. And so if we have a day what I'm hoping is that we have a day like that Monday of the finals, that I'm hoping that we are able to go over, do a question and answer thing, and then I'll upload those so you can have the latest answers in preparation for the final. Okay? So any questions on that? Hey, Renell, so I was telling these guys that I found out that the Roxy in Holbrook is doing a special showing of the Avengers.
Oh, really?
Yep. And so I tried to take my dual enrollment calculus class on a field trip. And would you believe Lance Vaturas turned me down?
Oh, I can't believe it.
Yeah.
Vaturas.
Anyway, so in front of these guys right here, these hardworking calculus students, I want to ask you, I think we need to have a Talon field trip of some kind, either at the beginning of the semester or the end of the semester, where we have a party with lots of food and meet the professor. We need to do something. What do you think?
I am in. I would love it. I'll help host it. Maybe we can meet in the middle somewhere of all of our different sites, like maybe in Snowflake, because
Maybe
we've got
Snowflake.
John, St. John's. Hopi will be coming pretty far, but we could, she can maybe come down, Jada.
Not to pick on baseball, Toby, but those teams, they go drive everywhere all the time and miss other classes and whatever. So if they have to miss another class for my class one time in the whole year, I think we can justify that and just say, let's get together and have a party. So either at the beginning of the year to meet your professor in person, or at the end of the year and celebrate your success. And maybe
I
even
like that. Yes.
And have a talent award day that I've wanted, and recognize these students that are working hard and getting scholarships and all kinds of stuff. We could.
So it would be, it's such a great idea. It is really a great idea. I'd vote for the end of the semester to celebrate the accomplishments. Because kids, look at, I mean, if these three successfully make it through Calc 2, that is not something to sneeze about. That is a
Exactly.
big deal for a high school student.
And if we can give them a
Easy.
slice of pizza or
Yeah,
sub
exactly.
or something, I don't know.
Like some pizza and a pat on the back.
I'm feeling like my calculus students don't get enough credit here, so I appreciate you. So listening to my ear,
You are welcome. And I'm
your
imagining them eating pizza right now. I hope they can imagine it too. Maybe it'll make them feel a little better. So.
Yeah. So.
All right. I love
Anyway.
your idea, Mr. Strong. Let's
All
make
right.
it happen.
All right. Thank you. Have a
Thank
good day.
you.
Go
You
see
too.
Avengers this weekend, or I'm going to tell you who dies.
Don't be a spoiler. Don't be a spoiler.
That's mean. That's really mean.
Yeah, I saw that meme that says Doctor Strange has seen the end game 11 million times. Be like Doctor Strange and don't spoil the end. So, anyway, okay. Well, let's go back to our lesson. Do you guys have anything? What do you think about my idea of having some kind of a party?
I think it's a great idea.
Well, I do think that you guys work hard and you need some anyway. I would like to do more, but you know, we're all separated, so it would just be fun. Even one time a year, I don't think that's asking too much. So
Yeah, I think it'd be a good idea.
So it'll probably come about, you know, next year after you've all left, you know, so that's how it works. But okay, well, let's go back to 11.2. We are at the very bottom of the first column. So the parametric formula. Now, I will warn you that I've been having some problems with the touchscreen here today. So I had to actually teach my trig class from the desk. So I'm gonna try to go back and interface with the board here. So, all right. So the parametric formula so this is the second derivative in parametric form. All right. So it's so what you do is you take so it's dy dt, the derivative of that, over dx dt. So it's kind of weird because it's like the numerator is like the second derivative, but the denominator is just like the first derivative. Okay? So let's kind of see how it works here. So it's really kind of more like dy dx. We calculate that and then the derivative. I personally think that this is a little more clear, but this is not how your book phrases it, but it's how I phrase it, because this is how I think of it, is we find the dy dx like we did yesterday, and then take that derivative. So it's like the second derivative, and then put that over dx dt. Okay? And this is not the second derivative, but a first derivative. Okay, so let's, so the steps are, number one, you express y prime or dy dx in terms of t. All right, then, so dy dt would be the first derivative, so dy prime dt is the second derivative. So this is like finding the second derivative and then divide that by dx dt. Okay? All right. So here's my example. So here I have x equals t minus t squared, y equals t minus t cubed. So first Okay, what we did yesterday is we said dx dt, we take the derivative of x with respect to t. So that would be 1 minus 2t. dy dt, we take the derivative of y with respect to t, 1 minus 3t squared. All right, then dy dx was dy dt over dx dt. So 1 minus 3t squared over 1 minus 2t. Okay, so that's kind of what we did yesterday. All right, so questions so far? Okay, so now we take that derivative. So dy dt prime. So take the derivative of this. So we got to use the quotient rule. So that's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. All right, so then we simplify that. So if we distribute the negative 6t, we get negative 6t plus 12t squared. Distribute the negative and the negative 2. So it's like distributing a positive 2, and we get 2 minus 6t squared over 1 minus 2t squared. And then it looks like we have like terms here and here. So let's combine those, and I get 6t squared minus 6t plus 2 over 1 minus 2t squared. Okay, now the final step is that to now divide that by dx dt. So the 1 minus 2t, see when we put that in the denominator, see that becomes 1 minus 2t to the third. So see, I've highlighted the difference in these exponents because see this step was just the dy dx squared. So, I mean, dy dx, the derivative of it, dy prime dx. And then I divide that by dx dt. Okay? And so this would be my final answer. Okay, so any questions on that? All right, so let's try practice 2. And if you need me to go back to the example, just holler. Okay, so Weston, when you get dy dx, let me know.
Okay. This might be wrong, but I think it's 2 times the square root of t.
That's it. So 2 square roots of t, or 2t to the 1/2. Okay. All right. So everybody okay with that part? Anybody want me to go through that? All right. So now, Jada, when you have the derivative of that, let me know.
It would just be T.
It would be t to the negative 1/2. Because remember, you bring the 1/2 in front, which would cancel with the 2, but then the exponent, you subtract 1. So 1/2 minus 1 would be negative 1/2. So that would be t to the negative 1/2, or 1 over radical t. All right. So, Toby, what's the final answer?
I don't know if I did it right, but I got 2.
2 is right. Because, see, you take that and then divide by dx dt. So you have 1 over radical t divided by 1 over 2 radical t. Okay, when you divide a fraction, you multiply by the reciprocal. The radical t's are going to cancel, so you just get 2. All right, great job. All right, any questions on that? Okay. Oops. Whoops. Okay. All right. So now we're jumping to part 4, and here we're talking about the length of a curve. Now, we did arc length, is what we called it back in chapter 6, I think. But this is the length of a parametrically defined curve. So it's defined in parametric with parametric equations. And so then you say it's the length, it is the integral from a to b of the square root of dx dt squared plus dy dt squared. And actually, if you might think it has something to do with the Pythagorean theorem, you'd be right, or the distance formula. It's like the change in the x's squared plus the change in y squared is giving us that change there. So that's the arc length. And so then we're adding them all up from point A to point B. Okay? So, it says using the definition, find the length of the circle of radius r defined parametrically by x equals r cosine t and y equals r sine t from 0 to 2 pi. All right, so the t values are going from 0 to 2 pi. So those are our limits of integration from 0 to 2 pi. All right, so then we say, all right, so if x is r cosine t, then dx dt, we take the derivative. The derivative of cosine is negative sine. So negative r sine t. Okay, if y is r sine t, then its derivative is r cosine t. So we take dx dt squared, dy dt squared, And so then when we square that out to simplify, we get r squared sine squared plus r squared cosine squared. Well, if we factor out an r squared, then we get sine squared t plus cosine squared t. Well, what's sine squared t plus cosine squared t?
1.
1. So then we have the square root of r squared, which is just r. All right, now, the t is the variable here. R is considered a constant for this problem. So you think, well, what would be the integral of like 5? Would be 5x. So the integral of r dt, if t is the variable, then the integral is going to be rt. And we evaluate that from 0 to 2 pi. So now we replace t with the limits of integration. So we have r times 2 pi minus r times 0 which is 2 pi r. So what did we just prove? Well, what I proved is the formula for the circumference of a circle is 2 pi r. So if you ever wonder where that came from, it comes, well, one way it comes from is from calculus, okay? So again, so we have the parametric equations here. You take their derivative and then square them, and then put them in the formula and then integrate, okay? And really at this point, now this one, because it's the variables and I wanted to show you the formula, you couldn't put that in the calculator. But if you had numbers here, you could, okay? So let's try example for, or practice 4, excuse me. Let's see, is that, all right, Weston, when you've got it. Or when
I
you
got
have it.
4.
4? All right, let's see how it is. So first, your dx dt is going to be negative sine t. dy dt would be 1 plus cosine t. All right? So everybody cool so far? All right, so now you say the integral from 0 to pi of the square root of negative sine squared plus 1 plus cosine t squared. All right, so I saw you punch in the calculator. Did you punch in at this point or did you simplify down?
I just punched in that point.
Okay, and that's fine. That's fine. Okay, so if you simplify it, then you get sine squared plus 1 plus 2 cosine t plus cosine squared. And then sine squared plus cosine squared, once again, is 1. And so that does simplify the integrand quite a bit. Okay? So it makes it a little bit easier because you don't have all those nested parentheses, but really, it's okay. So you can put that in. Really, I don't even think I would do this using the power reducing formula. I would just put it in the calculator. And let's see, we get 4. Okay. Now, the other trick that you can do is, let's say if you're having a hard time setting it up, see, instead of like going from 0 to pi, see, you could go from halfway, from 0 to pi halves, and then double it. So you could go, see, it's asking for this length here from 0 to pi. So you could go from 0 to pi halves and then multiply by 2. But you want to graph it and make sure it's symmetrical. All right, so any trouble with the calculator? Any problems with this one? Jada, did you get it? Okay. Toby? Okay. All right, well, that's it for 11.2. All right, so I would like us to start with at least introduce 11.3, because once again 11.3 is a trig section. Okay, so there's no calculus in the next section. This is on polar coordinates. So this is kind of a review of polar coordinates. And then when we do 11.4, then it will be doing some calculus on polar coordinates. Okay? So a lot of this, if you need a refresher, I think the polar coordinates in the trig book, it's actually explained a little bit easier, but whatever. So if you remember polar coordinates, this is what polar graph paper looks like. And so you have your angle in degrees or radians, and then you measure out this is the radius, or how many radii you go out. So 1, 2, 3. So you find the angle, and then the radius, and then that's how you graph. This is called the pole, what we would normally refer to as the origin. The positive x-axis we refer to as the polar axis, because everything is measured up from the positive x-axis or polar axis. All right, so the polar coordinate system serves as a means of locating points in a plane, but instead of an x value and a y value, points are in the form r theta. And usually when you're graphing, you find the angle first, and then you count out the radii. So, for example, 3.5 pi, so you would measure over to pi would be over here, and then 1, 2, 3.5. Negative 2 pi thirds, you find pi thirds, or 60 degrees, and then if your r is negative, then you go backwards. 1, 2, so it would be over here. 300, okay, so you find 300 degrees, which would be down here. and then you count out 1, 2, 3. All right, any questions on that? All right, so you guys graph those, please. All right, so the first one, the blue, 3 pi 4, so it would be this angle, and then you count out 2, 1, 2. All right, 3.5, 270. 270 is down here, so 1, 2, 3.5. And then the last one, -1, 4 pi thirds. So you do 4 pi thirds, which is down here. Let's see, 1/3, so right here. But then it's -1, so you go backwards up here. All right. Any questions on graphing the points in polar mode? Okay. All right, so polar coordinates are not unique. Now, that's different than, see, in XY, if I put a point in the XY plane, there's only one coordinate pair for that. There's only one X and one Y value there could be. But if I put a point in the polar grid, there's several ways I could represent it. The easiest is if, like, let's say you have 2 and 0 degrees. Well, if I just add 360 to the angle, so to 360 degrees, that would be the same point. So anytime you add 360 or 2 pi to the angle, you get the same point. So that's and there's other ways too. All right, so it says find all the polar coordinates of the point 2 pi 6. All right, so if you imagine going up pi 6, all right, then going out 2, that would be one way to do it. But if I go down here, pi 6 this way, so that would be 7 pi 6, and then go backwards 2, that would hit me up to the same point. So -2, 7 pi 6, or +2, positive pi 6. Okay, and then anytime you add, so if you're in radians, you can add 2 pi to the multiples of 2 pi. So 2 in pi to either angle, and that would give you other ways to represent it. And if it's in degrees, it would be plus 360 n. Okay? All right, so see if you can do practice 1. All right, so Jada, when you've got it.
Okay, I'm not sure. I think I got stuck.
Okay. So here, so the way I would do to start with this is probably graph it so you can see. Okay. But see, if I take this graph here and if I add 2 in pi, then that's going to be another equivalent angle. So just add multiples of 2 pi to this angle. All right. All right. Then see, if I go around to the other side, if I add pi to this, and then I change the sign of this, then that's going to give me an angle on the other side. So here, so here's like say pi thirds, and then -1 would be down here. So that's the same thing as if I go to 4 pi thirds and then +1. Does that make sense? And then by adding the 2 in pi, you're saying if I just go around the circle, I'm going to get the same point.
Okay, yeah, I got the first one, but I didn't get the second one.
Okay, but does it make sense that if you add pi? Okay.
Yeah.
All right. All right, so now to graph polar equations, remember r is the radius or distance from the pole, and theta is the angle from the polar axis. All right, so if I wanted to graph all of the points that had an r of 1 or -1, then see if it could be any angle. So if I just go out 1 radii, then it's going to be a circle. Because that's going to be all the angles that have, and then the r is going to be 1 or -1. Okay? Or if I'm given an angle, let's see. If I'm given an angle as pi 6, but the r could be anything, then that's going to be a line. Because see, I would go up, measure up pi 6, but see, the r could be anything. And so it's going to be any value positive or negative along that line. All right, so try practice 2. All right, so Weston, r equals 6. What is that going to look like?
It's a circle around the sixth. Yeah.
Yep. All right, and Tobias, what about theta equals 120 degrees?
So it's like a line going down to the right, and it's, I don't really know how to explain this. Yeah, like that.
Yeah. So you measure up from here 120 degrees. So this is, you're measuring from the positive x-axis. So that's your 120. But then since we don't know what r could be, it could be anything. So that's why it's on that line. Okay. All right. So now to graph a polar inequality, then this is where you shade the appropriate area. Okay. So the answer is going to be usually shaded. So if I want all the r's between 1 and 2 and all the thetas between 0 and pi halves, then see that's going to look like this. So the r's are between 1 and 2 and the angle's between 0 and pi halves. So it's going to be this little wedge right in here. Does that make sense? Okay. All right, let's try another one real quick. Oh, I guess we'll just do the practice. So r between -3 and 2, and theta is pi fourths. What would that look like? All right, so Jada, what do you think that would look like?
I don't know how to explain it. Like,
Okay, so I guess I could show the picture and you tell me if this is what you have. So here theta is pi fourths, so that's 45 degrees. And then the r is between -3, so that would be from back here to +2. So this would be a line segment there. Okay. Do you have that?
yeah, so like I wasn't sure because the last one you colored, I just got a line, so I wasn't
Yeah,
sure.
the whole area. Yeah, so
Yeah.
this was just a line segment. So
Okay.
sometimes you do if the angle is between like say pi halves and pi, then you might like shade that area or something like that. So anyway, all right. Well, this is a good place to stop. So let's call it for the day. Does anyone have any questions? Okay, so Toby, you got the message that I open up 3 quizzes for you. And then when you finish those, let me know and I'll open up the next 3 or something like that. Okay? But I don't want to open up too much and overwhelm you. Okay? So we'll just do what we can. So you guys have a great weekend. I really won't spoil. I'll be like Doctor Strange. I won't spoil the end game for you if you don't see it. But anyway, but you guys have a great weekend, and we'll see you Monday. Next week's our last full day of our last full week